This video is about frequency in discrete time. An intuitive understanding of this concept helps when studying digital signal processing, especially as a complement to purely mathematical descriptions. But before moving on to normalized frequencies, let's review the ordinary notion of frequency for a continuous time signal.
Here is a continuous time sinusoid, or rather cosine to be precise, although it doesn't matter much for this example. The unit on the x-axis is seconds, and the signal completes 1 cycle per second. We would say that this signal has a frequency of 1 cycle per second, or more commonly, that the signal has a frequency of 1 Hertz. If the signal completes 2 cycles per second, the frequency is 2 Hertz. On the opposite end, if the signal takes 2 seconds to complete the cycle, or equivalently, if it completes half a cycle per second, the frequency is half a Hertz. If the signal is a constant, we say that the frequency is 0, and this is the lowest frequency that we can have. At the other end, we already saw a signal with a frequency of 2 Hz, but we could have naturally chosen a signal with 4 cycles per second, or that is 4 Hz, or perhaps 8 or 16 Hz for that matter. The point here is that there is no highest frequency that a continuous time signal could have.
However, this observation surprisingly fails to hold for a discrete time signal. And this has important implications for discrete time and digital signal processing.
A discrete time signal is a sequence of values enumerated by a discrete integer parameter, called n in this example. If all other samples are the same as they are here, we say that the signal has a normalized frequency of 0. And we'll use the Greek letter ny to denote normalized frequency, and I will explain why we refer to it as normalized frequency in a little bit. But for now, it's helpful to just think of it as the frequency of a discrete time signal. If the signal is a discrete time sinusoid with 8 samples or signal values per cycle, we say that the normalized frequency is 1/8, corresponding to 1/8 cycle per sample. The unit of frequency in continuous time measured in seconds is Hertz, but normalized frequency is unitless because we don't assign a unit to the sample index n. It's just an enumeration of samples. And if the signal completes a cycle in 4 samples, the frequency is 1/4, and if a cycle completes in only 2 samples, the normalized frequency is 1/2. The question is, though, where do we go from here? We could in principle consider a signal that completes a cycle every sample, and say that it has a normalized frequency of 1. But then we may also ask what separates this signal from the signal with a normalized frequency of 0. And the honest answer is nothing really.
And the question then becomes what, if anything, we should do about that. We may choose to say that a discrete time signal simply cannot have a frequency which is larger than 1/2. We could also allow arbitrary normalized frequencies, but then we must accept that they do not yield unique discrete time signals. And in all honesty, it really doesn't matter which point of view we take, as long as we're consistent and know what we're talking about.
We'll dig a little bit deeper into this in a moment, but let us first address the question of why we use the term normalized frequency. If we return to the 1 Hz continuous time signal and create a discrete time signal by sampling this signal 8 times a second, we see that we obtain a discrete time signal with a normalized frequency of 1/8. In other words, the normalized frequency is given by the frequency of the original signal normalized by the sample frequency, and hence the name normalized frequency. If the original signal's frequency is 2 Hz and the sampling frequency is 8 Hz, or 8 samples per second, the normalized frequency becomes 2/8, or 1/4, and we can see that we get 4 samples per cycle of the discrete time signal. If the original signal's frequency is 1 Hz and the sampling frequency is 4 Hz, the normalized frequency is again 1/4, and the samples may have been collected at different rates, but we are dealing with the same sequence of samples as far as the discrete time signal is concerned.
In all of these examples, the normalized frequency is simply the frequency of the continuous time signal normalized by the sample frequency. But let us return to the case of a normalized frequency of 1.
We would get this if we, for example, started with a signal with a frequency of 8 Hz and also sampled it at 8 Hz. With the interpretation of normalized frequency as simply a ratio of an original frequency over a sampling frequency, a normalized frequency of 1 makes perfect sense. But this example again shows that for the resulting discrete time signal, the normalized frequency is also 0. In fact, any two normalized frequencies that differ by an integer amount will yield the same discrete time signal. If we have a continuous time signal of 5 Hz and sample this signal at a sample rate of 4 Hz, we get a discrete time signal with a normalized frequency which is 5/4. But a normalized frequency of 5/4 should, by this logic, be equal to a normalized frequency of 5/4 minus 1, or simply 1/4. And this is also what we get if we were to sample a signal of 1 Hz at the same sample rate. In other words, the equivalence of normalized frequency 5/4 and 1/4 implies that signals at 1 Hz and 5 Hz yield the same discrete time signal when sampled at 4 Hz. And this is a phenomenon called aliasing. We can extend the example by also considering a signal of 3 Hz, sampled again at 4 Hz. We still get the same samples, but in this case, our normalized frequency is 3/4, and by the previous logic, this should be equal to 3/4 minus 1, or minus 1/4. But this forces us to tackle what should we mean by a negative frequency.
Unfortunately, it isn't easy to illustrate the concept of negative frequencies using graphs of real-valued signals plotted against time or sample index. But luckily, it can be illustrated using the spinning wheel analogy.
So let us consider a wheel that completes 1 cycle per second, or in other words, that spin with a frequency of 1 Hz. In this analogy, a frequency of minus 1 Hz would correspond to a wheel spinning at the same speed but in the opposite direction. The direction of motion that we associate with a positive frequency is somewhat arbitrary, but convention has it that we associate counterclockwise movement with positive frequencies and clockwise movement with negative. If we sample this motion at a sample rate of 8 Hz, we obtain a discrete time sequence with a normalized frequency of 1/8, or 8 samples per second. If we were to sample the same motion at 4 Hz, we would get a normalized frequency of 1/4. Sampling at 2 Hz gives a normalized frequency of 1/2, and finally, sampling at 1 Hz gives us a normalized frequency of 1, which we already concluded was equivalent to a normalized frequency of 0, or no movement at all for the discrete time signal, which is also what we see here. But let's now consider sampling at a sample rate somewhere between 1 and 2 Hz, say at 4/3 Hz. If we study the sequence of discrete time samples obtained in this case, we may reasonably conclude that we have a normalized frequency of minus 1/4. We have 4 samples per cycle, but the motion is now clockwise instead of counterclockwise. If we compute 1/4/3 minus 1, we get, perhaps not surprisingly by now, minus 1/4, which is consistent with this observation. And you have most likely already seen this effect if you've ever watched a movie of, say, a rotating bicycle wheel. As movies are essentially a discrete sequence of image frames representing a continuous time world, we can, at certain sample rates and rotation speeds, end up in a situation where the wheel seems to rotate backwards, or stand nearly still. When we discretize, or sample a movement, we can from the samples alone only observe the fraction of a cycle that occurs between each sample point. And this is precisely the reason why normalized frequencies that differ by an integer amount are equivalent from the perspective of the discrete time signal. We simply cannot observe the number of integer rotations on top of this motion. When working with normalized frequencies, it's common to limit the range of normalized frequencies that we allow. We may, for instance, require that our normalized frequencies are in the range 0 to 1, which is equivalent to describing the fraction of rotation between 2 consecutive samples, counterclockwise, around the circle. We may also require normalized frequencies to be in the range minus 1/2 to 1/2, which is equivalent to describing the motion with the rotation either clockwise or counterclockwise around half of the circle. Both descriptions work, but the most common choice seems to be the latter. However, it's essential to note that both cases are in stark difference to the frequencies of continuous time signals, which, as we saw, can take on arbitrary values.
The key to understand here is that any normalized frequency in the chosen range is also representative for all normalized frequencies that we can obtain by adding or subtracting an integer from it. Another perspective is that each discrete time signal corresponds to a sampled version of an infinite number of continuous time signals that differ by multiples of the sample frequency.
Finally, when working with a real-valued signal, all we can view is the projection of the circular motion on the single axis. But this removes our ability to determine the direction of the circular movement, which limits us to normalized frequencies in the range 0 to 1/2. This is also the reason why I could not show you the notion of a negative frequency within the constraints of the first example. However, when working mathematically with these signals, it's really convenient to rely on the spinning wheel analogy and represent points on the circle using complex numbers. If we sample at 4 Hz, rotations of 1 Hz and of 5 Hz provide the same set of samples. A rotation of 3 Hz provide a clockwise motion of the same rate when sampled. But if we only consider the projection of the motion onto the x-axis, we obtain the same set of samples, and this is also what we saw earlier in the examples with the graphs.
The ambiguity between normalized frequencies will have several consequences when working with discrete time signals and systems. For example, the discrete time Fourier transform will, as a function of the normalized frequency ν, have to be periodic with a period of 1. Another consequence is that a discrete time system cannot have one effect for a signal of a normalized frequency of 1/4, and another effect on a signal of a normalized frequency of 5/4, as these two signals are, in reality, one and the same discrete time signal. The ambiguity between normalized frequencies also have several important real-life consequences. For example, if we sample a continuous time signal with a frequency f and we require that the normalized frequency falls within the range of 0 to 1/2, then we must ensure that our sampling frequency is at least twice that of f. Sampling at a lower sample rate would still give us a discrete time signal, but there would be an ambiguity regarding the frequency of the original signal. This observation is at the heart of arguably the most famous result in all of signal processing, the Nyquist sampling theorem. The sampling theorem essentially states that we can recover a continuous time signal uniquely from its discrete time samples if, and only if, those samples were collected at twice the rate of the highest frequency that we had in the signal. And this is why most digital music is sampled at 44.1 or 48 kHz, which is just about 2 times 20 kHz, or 2 times the highest frequency that is perceptible to humans. And this way we can recover all of the sounds perceptible to humans from the digital samples that we store, process, transmit using, for example, a streaming service. However, the details of the Nyquist sampling theorem and digital music are topics for another video.